All right, welcome everyone. So in this video, we are going to define an operation between two column vectors called the inner product or the dot product. And then we'll see how this relates to our previous discussion of magnitude of vectors and look at some properties of this operation. So let's consider two vectors u and v. These are n by 1 column vectors. So we have n rows and 1 column. So for example, vector v looks like v1, v2, all the way down to vn. And then we define the dot product of these two vectors u and v that we denote with a dot between them. And for anyone that's worked with vectors before, there are different ways that we can define a product of two vectors. So the dot product is going to be a product that results in a scalar. So we're going to take vector u and take the dot product with vector v. That we can write as the product of u transpose. So if u is an n by 1 column vector, u transpose is going to be a 1 by n row vector. So that's what u looks like. U transpose would look like over here. And we multiply this matrix by this matrix, this column vector over here, v1 up to vn. So the way that we would multiply these two vectors would be we take u1 times v1, u2 times v2, all the way up to un times vn. So we can only define the dot product if u and v are the same size. So in other words, using summation notation, we can write this as the sum as I goes from 1 to n of ui times vi. And again, the result in the end is a scalar value. So taking the dot product of two vectors results in a scalar. And this we call the inner product or the dot product of the two vectors. So let's take a look at an example before discussing some properties of the inner product. So if I have a vector u, which is in R3, which is the column vector 2, minus 5, 1, and a vector v, which is the column vector 6, 2, minus 7. And we want to calculate the dot product of these two vectors with each other. Then by definition, we take the first entries in each vector and we multiply them. So we take 2 times 6. And then we add to that the product of the second entries in each vector. So that would be the minus 5 times the 2. And then we add to that the product of the third entries. That would be the final entry in this case of 1 times minus 7. And then we add up all of these products. And in this case, that results in minus 5, the value minus 5. So for dot product and inner product, we get a scalar, and that scalar could be positive, that scalar could be negative, that scalar could be 0. Okay, now that we've defined the inner product of two vectors, let's take a look at some properties that this inner product is going to satisfy. So let's let vectors u and v and w be column vectors all in Rn. So they all have n entries. And let's let C denote a scalar. Then the first property is that if we take the dot product of u and v, it's the same thing as taking the dot product of v with u. So this we would say the inner product is a commutative operation. The order that we take the dot product does not affect the final result. And we can take a look at why that is true. This follows from the fact that multiplication is a commutative operation, multiplication of two scalars. So if I take the dot product of u and v, recall by definition that would be u1 times v1 plus u2 times v2 all the way up to plus un times vn. And these are products of two numbers. So we know that the order that we multiply numbers doesn't matter. So I could write u1 v1 as v1 times u1 plus v2 times u2, all the way up to plus vn times un. And now writing the inner product in this way, it's equivalent to saying v transpose times u, which is by definition v dot product with u. So that's a quick proof of the very first property that the inner product is a commutative operation. We have other properties that should be familiar to you. And so here we have like a distributive property. So if I take the sum of two vectors u plus v and take the dot product of that sum with a third vector w, this is equal to taking u inner product with w plus v inner product with w. The proof of this is in the text, but this is going to follow similarly to A. This is going to follow from operations and properties of addition and multiplication of scalars that we're already familiar with. A third property involves what happens if I take some scalar c times a vector u and then take the dot product of cu and a vector v. And we can move this scalar c around this inner product. So I could either first take the inner product of u and v and then multiply c, or I can take u with the inner product with c times v, and those are all going to equal if I first take c times u and then take the inner product with v. And a fourth property is that if we take the inner product of v with itself, we get something which is going to be strictly bigger than 0. And secondly, that the inner product of v with itself equals 0. That's only going to happen if the vector v is the 0 vector. And in the space below, we can see why this property holds, and that is if I take the dot product of v with itself, then this would equal v1 times v1 plus v2 times v2 plus all the way up to plus vn times vn. So in other words, it's v1 squared plus v2 squared plus v3 squared all the way up to vn squared. So if I'm adding a bunch of numbers raised to the second power, each of these numbers has to be greater than or equal to 0. So adding a bunch of numbers that are greater than or equal to 0 is going to result in a sum which has to be greater than or equal to 0. And the only way we get 0 is if v1, v2, v3, all of these entries are equal to 0. So in other words, the only way we get 0 is if the vector v is equal to the 0 vector. And now taking a look at property D, if we were to put the square root over this sum, then notice this looks exactly like what we just defined as the magnitude of v, the length of vector v. So there's a nice connection between inner products and lengths magnitudes of vectors. Namely, we can find the magnitude of a vector v by taking the dot product of v with itself and then taking the square root. So in other words, the magnitude of v squared is going to equal v dot v.